Okay, so we continue with our discussion on single mode states. What we looked at was initially number states of a single mode field, nket or Fock states, and then we looked at coherent states. So these coherent states, let me recall, are eigenstates of the A operator. We calculated the expectation value of the electric field of this state, and we found it is very similar to the classical electromagnetic wave. Expectation value goes as sin omega t minus kz. We also calculated the variance in the electric field, and we found that the variance was equal to that in vacuum. So this is the state which is closest to the classical electromagnetic field, and the variance, the relative variance, will decrease as you increase the amplitude of the electromagnetic field. As you increase mod alpha, which the electromagnetic field is proportional to mod alpha here, and as you increase the value of mod alpha, the field amplitude keeps on increasing, and the noise remains the same as the vacuum. So the field will appear to be almost noise-free at very high amplitudes, and hence that's a very good description of a classical field where you can sort of forget about noise. We also found that the two quadrature operators, we had calculated the noise and the expectation values of the two quadrature operators, and what we found is, let me recall the diagram that we had drawn. This is the x quadrature, this is the y quadrature. The field is represented by a circle. This is mod alpha, and let me recall mod alpha is equal to square root of n bar, which is equal to delta n. The fluctuations in number of photons in that state is square root of n bar. N bar is the average number of photons in that state. In the state alpha, there is an average number of photons, and this is the fluctuation is square root of the average number. And this is a circle of radius half. So in a way, we can actually interpret this figure as this length, the square of this length is actually n bar, which is the average number of photons. The square of this length is n bar, which is equal to the average number of photons in the state. And we can also look at this angle. This angle is the angle submitted by this diagonal, by this diameter at the center. You can interpret this angle as something like an uncertainty in the phase of the electromagnetic field. And this, along the length of this, as an uncertainty in the number of photons in that state. Just like you can interpret delta x, delta y as the quadrature operators, where the uncertainty is in x and y quadratures, I can also interpret this as this being the approximately proportional to the uncertainty in the number of photons, and this angle being the uncertainty in the phase of the electromagnetic field. So you can actually write down an approximate relationship between these two. If I assume mod alpha to be large, then this angle, suppose I call this delta theta. How much is delta theta? This by this distance, so half by square root of n bar. This half divided by this distance, which is mod alpha, which is square root of n bar, and which is equal to 1 by 2 times delta n. So this is something like delta n into delta, let me write this delta theta, some kind of an uncertainty relationship connecting the number of photons in the state, the fluctuations in the number of photons in the state, to the fluctuations in phase. Note that this circle has the same diameter irrespective of the value of mod alpha. So if you look at two states, one which is a small mod alpha and one which is a large mod alpha, this phase uncertainty is much larger here compared to this. The vacuum has this the same noise, vacuum noise all the time. Wherever the mod alpha value is, this particular state with smaller volume mod alpha, has a larger phase uncertainty compared to this. Because actually delta n is becoming smaller as you come to closer numbers here, closer values, and so delta theta is actually increasing. Okay? So this is also a good picture to sort of have in mind that the number of photons in the state, the fluctuation in the number of photons and the fluctuation in phase are sort of related through a kind of an uncertainty relationship. Because this picture will become useful to us when we go into the next state, what are called as squeeze states. Okay, yeah. I can interpret this distance, square of this distance is the average number of photons, because mod alpha square is n bar. I can interpret this angle subtended by this circle on the x on this origin as if it is an uncertainty in phase. So if I look at two coherent states, one with small value of mod alpha and one with large value of mod alpha, because the vacuum noise is the same in both cases, the angle subtended by this circle here is larger than the angle subtended by this circle. So this has more phase noise than this one. That is because delta n for this is larger, because n bar for this is smaller. Sorry, delta n is smaller here. And so delta theta is larger essentially, because these two relations approximate the relationship delta n delta theta is equal to half. So I can sort of interpret the this along the radial direction as an uncertainty in the number of photons, and this distance to be approximately proportional to the uncertainty in the phase of the electromagnetic field.
So, but according to this, it should be the same always, because the circle is of the same dimensions wherever we go. So uncertainty in number of photons is also 1, and number of in phase is also.
No.
You said we can interpret this, the diameter along one of the axes, you said, can be interpreted as uncertainty in phase. I mean that.
This angle will decrease as you go to larger and larger value of n bar. As you increase the number of photons in the state, in this coherent state, the phase uncertainty starts to reduce. And so with large values of mod alpha, which is very close to classical states, the phase uncertainty is very little. So you can very well define a field as E0 cos omega t minus kz or sin omega t minus kz. Okay, now we go to another class of states called squeeze states. We are still looking at single mode states. We are still looking at states in which there is only one mode excitation, because after all this discussion we'll come to what are called as multimode states, where I will have fields in more than one mode. Right now there is only one mode, which means one frequency, one propagation direction, and one polarization state. Now if you recall, we had this relationship between the uncertainty in the two quadratures. The x quadrature and y quadrature have to satisfy the uncertainty relation, and when delta x delta y becomes equal to 1 by 4, these are called the minimum uncertainty states, because this is the minimum value of uncertainty product that these states have. And coherent states have equal uncertainties in both x and y. Delta x is equal to half, delta y is equal to half. This is what we have derived. So those are states in which the uncertainty in x and y are equal. But there is no requirement that delta x or delta y need not be less than half, because all that I need is the product must be greater than or equal to 1 by 4, and for all minimum uncertainty states the product must be equal to 1 by 4. So I can have states in which one of the quadrature has less uncertainty than the other quadrature. And these are called squeeze states, because in the phasor diagram they will not be circles anymore, but they will be ellipses, squeezed in one direction compared to the other. So they are called squeeze states, and so we will look at these squeeze states. So I can have reduced uncertainty in one of the quadratures, and this becomes very interesting for many applications of these kinds of non-classical states of light. Okay, to introduce squeeze states, before this, I forgot. Okay, let me try to answer one question, and that is which was posed at the end of the last class or just after the class was over, that what is the picture we are using in discussing these coherent states? Have we used Heisenberg picture or have we used Schrodinger picture? Yes. Please note, we have written alpha as sigma Cn n, and we have written E vector as I E naught by 2 A exponential minus I omega t minus kz minus A dagger exponential I omega t minus kz. Yeah, we have used Heisenberg picture because we have kept the alpha state to be independent of time, and we have taken all the time dependence into the operator E. So suppose I were to use the Schrodinger picture, how would I approach this problem? Because there are places where you would like to use the Schrodinger picture, sometimes you would like to use the Heisenberg picture. So let me do an analysis now of the same problem in the Schrodinger picture, and I should get the same expectation value of electric field, irrespective of which picture I use. So in the Schrodinger picture, alpha will become a function of time and E will be independent of time. So E operator, electric field operator, will be I E naught by 2 A exponential I kz minus A dagger exponential I kz. A and A dagger are constants. That is, at t is equal to 0, the electric field of the two pictures match, and alpha is a function of time. Now, how do I find out how this alpha state varies with time? Can one answer? How do I find out how alpha state will vary with time? Here is alpha at t is equal to 0. So alpha t will be equal to Cn exponential minus I E n t by h cross n. Each one of the Fock states evolves in time as exponential minus I E n t by h cross, where E n is n plus half h cross omega, h cross omega. Is that clear? So this is the state at t is equal to 0. As a function of time, this is the evolution. So I can actually substitute for En into this equation and get alpha of t is equal to sigma Cn exponential minus I n plus half omega t n, which is equal to minus I omega t by 2. Let me substitute for Cn. So minus mod alpha square by 2 sigma alpha is per n by square root of n factorial exponential minus I n omega t n. I have replaced En by n plus half h cross omega, and I have just taken this out, and this is equal to minus I omega t by 2 minus mod alpha square by 2 sigma alpha exponential minus I omega t raised per n by square root of n factorial n. So this is actually because if alpha is given by without this factor, alpha is just this without this factor. So if alpha has changed to alpha into exponential minus I omega t because the mod alpha square remains the same as before. So what has happened is the coherent state evolves into a new eigenvalue alpha exponential minus I omega t. In fact, what is A of alpha t? So alpha t is given by here. So this is equal to sigma Cn minus I n plus half omega t A times n. So A alpha t minus mod alpha square by 2 sigma let me just write exponent my so alpha raised per n by square root of n factorial exponential minus I n plus half omega t square root of n minus 1, which is equal to minus mod alpha square by 2. Okay, so this becomes alpha raised per n by square root of n minus 1 factorial with the square root of n here minus I n plus half omega t n minus 1. So I can write this as alpha times exponential minus I omega t into minus mod alpha square by 2 sigma alpha raised per n minus 1 by square root of n minus 1 factorial. Okay, so I write this as alpha exponential minus I omega t raised per n minus 1. I've taken out one alpha from here and one exponential minus I omega t from here. So I'm left with actually into minus I omega t by 2. No. So what is this? This is nothing but alpha t is this minus I omega t by 2 into this. So this summation is still the same as before. So this becomes simply, if you look at this expression for alpha t, you have exponential minus I omega t by 2 into this ket. This ket has a sum over n or sum over n minus 1, it's the same. So exponential minus I omega t by 2 minus alpha square by 2 alpha exponential minus I omega t raised per n minus 1 by n minus 1 factorial into n minus 1 ket, and that's alpha t. So it's essentially the eigenvalue of this as a function of time keeps on changing to alpha exponential minus I omega t. So the state is changing with time now. The field operators are constant with respect to time. Now my objective is to calculate the expectation value of electric field and to show you that it is the same as we had obtained using the Heisenberg picture. So I am given alpha t, I know the electric field expression, so let me calculate the expectation value. Expectation value of electric field is equal to alpha E alpha. So this is equal to sigma Cm star exponential I m plus half omega t m, this is the bra alpha, into A exponential I kz minus A dagger exponential minus I kz into sigma Cn exponential minus I n plus half omega t ket n. This is ket alpha, this is bra alpha. The summation indices are different. This is ket alpha, this is bra alpha. And that is the electric field operator with, there is I E naught by 2. So this is equal to I E naught by 2 sigma m sigma n Cm star Cn exponential I m minus n omega t into now exponential ikz m a n minus exponential minus ikz m a dagger n. Okay, so this mn, this is the man from here first term and m a dagger n from the second term. Now can you tell me how much is this? A operating on n is square root of n minus 1. So m n minus 1 is, so this is square root of n delta m n minus 1, and this one is if you operate with a on n, you get square root of n minus 1. M n minus 1 bracket is delta m n minus 1. A dagger on n is square root of n plus 1, n plus 1. M n plus 1 is delta n plus 1. So because of these two Kronecker delta functions, the double summation will reduce to a single summation. So what will I get? If I use this delta function, the Kronecker delta functions, I will get expectation value of E is equal to I E naught by 2 sigma m. So let me put in the first case, in the first term I will have m is equal to n minus 1. So C n minus 1 star C n, m is n minus 1. So I get exponential minus I omega t. Then I will have exponential ikz, and the second term will be minus I E naught by 2 sigma n Cn plus 1 star Cn exponential I omega t into exponential minus ikz. This is square root of n and this is square root of n plus 1. So this is I E naught by 2. Now both the c's contain exponential minus mod alpha square by 2. So the product becomes minus mod alpha square sigma alpha star raised to the power n minus 1 by square root of n minus 1 factorial alpha raised to the power n divided by square root of n factorial square root of n exponential minus I omega t minus kz. I E naught by 2 Cn minus 1 star is exponential minus alpha mod alpha square by 2 alpha star raised to the power n minus 1 by square root of n minus 1 factorial. Cn is exponential minus mod alpha square by 2 alpha raised to the power n by n factorial square root. And second term is minus I E naught by 2 sigma, okay, you will again get minus mod alpha square sigma alpha star raised to the power n plus 1 by square root of n plus 1 factorial alpha raised to the power n by square root of n factorial square root of n plus 1 into exponential I omega t minus kz. So this is I E naught by 2 minus mod alpha square. So let me take out alpha from here, alpha, and I'll be left with sigma mod alpha square raised to the power n minus 1 by n minus 1 factorial. The square root of n removes 1 of the square root of n from here to makes it square root of n minus 1 factorial into n minus 1 factorial square root is n minus 1 factorial. 1 alpha I have taken out. So alpha star raised per n minus 1 into alpha raised per n minus 1 is mod alpha square raised per n minus 1, and I will have exponential minus I omega t minus kz. And the second term will be minus I E naught by 2 exponential minus mod alpha square. Now I take out alpha star, and I will get sigma mod alpha square raised per n by square root of n factorial, sorry, just n factorial into exponential this factor. Exponential, this is I chi actually. I've taken out alpha common out here to get mod alpha square is n minus 1. I've taken out alpha star common here to make it mod alpha square is per n by n factorial. What is this? And what is this? X raised per n minus 1 by n minus 1 factorial summation e to the power x. This is also e to the power mod alpha square. This is e to the power mod alpha square. This is e to the power mod alpha square, and that goes off with this e to the power minus mod alpha square. It cancels off, and I am left with a much more simplified form. I E naught by 2 alpha exponential minus I omega t minus kz minus I E naught by 2 alpha star exponential I omega t minus kz. The two summations give you exponential mod alpha square, which then cancels off with exponential minus mod alpha square. So if, as before, I write alpha is equal to mod alpha exponential I theta. So expectation value of E becomes I E naught by 2 mod alpha into exponential minus I omega t minus kz minus theta minus exponential I omega t minus kz minus theta. This is alpha star, so I get a minus theta here, and this is nothing but 2I sine with a minus sign, minus 2I sine omega t minus kz minus theta. So this becomes E0 mod alpha sine exactly as before. This was a little more involved derivation through the Schrodinger picture. The Heisenberg picture was very quick. You could immediately calculate the expectation values through using the operators which were time dependent. Here the states are time dependent, and we have to go through a little bit of procedure, but the expectation values are the same. So I can actually discuss the entire procedure either in terms of Schrodinger picture or the Heisenberg picture. In some situations maybe one is easier, and so I will use that, but I thought I will just show you that I could have solved the coherent state problem, expectation values of electric field, using the Schrodinger picture, and I will exactly get the same equations. All the expectation values will be exactly the same. The only difference is in one case the operators are time dependent, and in the other case the operators are time independent. Okay, so I thought this a nice exercise to use the two pictures and to compare the values, which are of course expected to be the same. Okay, so now we go back to squeeze states. So as I was mentioning, the uncertainty products between x and y quadrature, minimum value is 1 by 4, but there is no restriction on either delta x or delta y. And squeeze states are states in which the uncertainty in one of the quadratures is less. These are called quadrature squeeze states. For example, if delta x could be less than half or delta y could be less than half, and I will get the two quadrature squeeze states. So let's try to discuss these states. And again, in single mode, I still have only one frequency, one mode of propagation. Now, to discuss squeeze states, we introduce another operator. We introduce an operator which is B is equal to mu A plus nu A dagger. Linear combination of the annihilation and creation operators. So B dagger will be mu A dagger plus nu A. Now, in general, mu and nu are complex, but to have a simplified analysis, I will assume mu and nu are real. But in general, mu and nu are complex. Okay, so I will assume mu and nu are real in the analysis that we are doing just to simplify the mathematical equations here. So what is B dagger? This is equal to mu A plus nu A dagger, mu A dagger plus nu A, which is equal to mu square AA plus mu nu, sorry, AA dagger, AA plus mu nu A dagger A plus nu square A dagger A dagger A. Mu square A dagger plus mu nu AA plus mu nu A dagger plus nu square A dagger A. So what is A dagger? Is 1, and this is 0, and this is minus 1. Okay, I also restrict my mu and nu to the fact that mu square minus nu square is equal to 1. And so this becomes equal to 1. Just like AA dagger is equal to 1, BB dagger is also equal to 1. So I'm looking at states. I'm looking at an operator B is equal to mu A plus nu A dagger with the condition mu square minus nu square is equal to 1. So if mu and nu are real, I can represent this by a single condition. For example, mu could be written as cos hyperbolic sigma and nu could be sin hyperbolic sigma. They will satisfy this equation exactly. So later on I will put these numbers, this mu is equal to cos hyperbolic sigma and nu is equal to sin hyperbolic sigma. So that this condition is satisfied, I don't have to keep track. So I could have written A cos hyperbolic sigma plus A dagger sin hyperbolic sigma. Now please note, where did you get this hyperbolic function solutions in nonlinear process? Parametric down conversion. This operator is actually will come there in the parametric down conversion process. In the quantum mechanical analysis of the parametric down conversion, we will bring in these operators because they contain cos hyperbolic and sin hyperbolic functions and they satisfy this condition. Okay? So this is the B operator. You can actually invert these operators to write A and A dagger in terms of B and B dagger. So let me just give you the equations here. A is equal to mu B minus nu B dagger and A dagger is equal to mu B dagger minus nu B. If mu and nu are complex, I need to keep track of the phase of mu and nu. So I could later on I will write mu is equal to cos hyperbolic sigma and nu is equal to So these satisfy. And you also see it here, mu plus nu is, how much is mu plus nu? Not I sigma, sigma. And mu minus nu? Okay, this is assuming, yeah, this relations for mu and nu, okay. Okay, now we define, so B and B dagger operators satisfy similar equations as A and A dagger operators. Just like we defined the coherent state as an eigenstate of the A operator, we will define the squeeze state as the eigenstate of the B operator. So let me look at a state which I call as beta state. So beta is the eigenvalue of the B operator. And beta in general could be complex. But again, to keep the analysis simple, I'm going to assume beta is real. The mathematics that we will do will be very general, except that if you assume beta was not a complex, not real, or mu and nu were not real, you will have to be dealing with mu star, nu star, beta star, etc. So just to keep the mathematics a little more compact, I'm assuming mu and nu are real and beta is real. Okay, so these are states. So let me calculate the expectation value of electric field in this state. Suppose I were to generate a state which happens to be an eigenstate of the B operator for some value of mu and nu and with some eigenvalue beta. So in this state, let me calculate. Now remember, E is given by I E naught by 2. So this is beta. Now we go back to Heisenberg picture. So A exponential minus I chi minus A dagger exponential I chi. So let me recall, E naught was equal to square root of 2 h cross omega by epsilon 0 v, and chi is omega t minus kz. We are looking at a mode propagating along the z direction at a frequency omega and polarized, linearly polarized in some direction. So we are forgetting about the vector nature of the electric field operator here. So I need to calculate beta A beta and beta A dagger beta. So beta A beta is beta. Now let me substitute for A. A was shown to be mu B minus nu B dagger. So because beta B beta is equal to beta beta, what is it's supposed to be beta star beta, and I am assuming beta to be real, so I am assuming beta beta. Otherwise I have to keep beta star there. Okay, so what is the value of this? And beta is normalized. Beta beta is equal to 1. Mu minus nu into beta. Right? Because B beta is beta, beta dagger beta, B beta is beta, beta still. So if it was not, I would have got mu beta minus nu beta star. What about beta? A dagger beta. So this is beta mu B dagger minus nu B, which is equal to same, because beta is real. Otherwise I would have got here mu beta star minus nu beta, which is different from the other one. So I've got expectation value of A and expectation value of A dagger in this state. So what is the expectation of the electric field? So expectation value of electric field is equal to I E naught by 2. So mu minus nu beta exponential minus I chi minus mu minus nu into beta exponential I chi, which is equal to I E naught by 2 mu minus nu into beta exponential minus I chi minus exponential I chi, which is equal to, so this is minus 2I sine chi. So I get E naught mu minus nu beta, which explicitly in terms of time and space dependence is actually okay. So the eigenvalue beta appears here, and so does the mu and nu factors here, because the B operator is defined in terms of mu and nu, and the eigenvalue is beta. And the expectation value of the electric field goes exactly like a sine omega t minus kz, just like a classical field. But what would be interesting is to see what is the variance in the electric field as a function of time. In the coherent state, how did the variance vary with time? The variance of the electric field in the coherent state, it was independent of time, it was constant. Here I will show you that the variance depends on time, and there are times in which the uncertainty in the electric field is less than what you are getting in the coherent state, at the expense of increased uncertainty at other times in the state, because delta x delta y has to be greater than or equal to 1 by 4. So I will not be able to, I can't reduce the uncertainty at all times, or which means for both quadratures, I can only do so for one at the cost of the other. Now, I need to calculate the expectation value of E square. So what I need to do is this equation. Yes.
So as we have delta x into delta is governed by the Heisenberg uncertainty as well. Similarly, if there is a variance in the electric field, what should be the corresponding
conjugate variable?
Yes.
That is vector potential actually here. So we are not looking at the corresponding conjugate variable of the electric field here. We are looking at the two quadrature operators of the electric field itself. But the variances between these two get distributed depending on the state of the electromagnetic field.
In a case when the variance of electric field becomes less than the vacuum fluctuation, as you're saying,
at a given times.
at a given time,
Yeah.
then the variance in the vector
Conjugate variable will be much higher. Yeah.
So what would it mean?
No, but if I'm measuring the electric field, or if I'm measuring something related to the electric field, and if the variance in the electric field is less, I will detect less noise. Photo detection process, for example, depends on the electric field. And I will a little later introduce the concept of what is the meaning of photo detection. When light falls on a photodetector, what is happening, and how do I calculate quantum mechanically this issue of detecting photons when they arrive on a photodetector? So it depends on the electric field. So if the electric field has less variance, it will lead to a certain effect on the photodetection process itself. So for example, normally you don't measure electric fields, you measure the square of the electric field. But there are techniques using homodining, etc., in which you can actually measure either of the quadrature. So I will come to this a little later. Okay? Yeah, Vishwesh.
So why is the coherent state defined as an eigenstate of A?
No, I have defined a state.
Why? How do I know that it's the corresponding coherent state in the classical?
No, this was introduced by Roy Glauber in the early 60s. If you calculate the state generated by classical current, through a detailed analysis, one can show it's a coherent state. Now I did not derive that I will get a coherent state. I've started from the coherent state, I've looked at a state which happens to be the eigenstate of the A operator, and then I calculated the properties of the state. I have not derived the coherent state. But if you try to obtain what is the state generated by a classical current source, it is like a coherent state. So which we have not done in the class here. No. Okay, so what I need to calculate are these quantities. Beta, so it becomes minus E naught square by 4. So let me just write the equations, and we will discuss this later next class. So A exponential minus I chi minus A dagger exponential I chi whole square beta. So I need to calculate all these quantities. So this is minus E naught square by 4 beta A square exponential minus 2 I chi plus A dagger square exponential 2 I chi plus A dagger minus A dagger minus A dagger A. Now, so I need to calculate things like beta A square beta, beta A dagger square beta, beta A dagger beta, and beta A dagger A beta. And I have to substitute the expressions for A in terms of B in those equations. So for example, if I need to calculate beta A square beta, so this will be beta. Now A is mu B minus mu B dagger square beta. So this is equal to beta mu square B dagger square plus mu square B dagger square minus mu nu B dagger minus mu nu B dagger B. So what is beta B square beta? It's simply beta square, because beta is beta beta, and one more B if you operate, you get another beta. So you will get mu square beta square plus nu square beta square. I would have got beta star square, but I am just getting a beta square because beta is assumed to be real, minus mu nu B dagger on beta is not beta beta. So I have to use the commutation relation between B and B dagger. So B dagger is equal to 1, implying B dagger minus B dagger B. So this B dagger is 1 plus B dagger B. So I get minus mu nu minus, there is another mu nu B dagger B, so I get 2 mu nu beta square. Please note, B beta is beta beta. Beta bra B dagger is beta beta bra. B dagger beta is not equal to beta beta. So this gives me, so let me, this is equal to beta square into mu square plus nu square minus 2 mu nu. Now let me give you the expressions for the others, and I will leave it to you to please go back and calculate. So it's the same as this. Okay, why not I leave it? Please calculate the other two terms. That is beta A dagger beta and beta A dagger A beta. And we will get finally an expression for E square expectation value, from which we will be able to calculate the variance in the electric field. And then I will discuss this variance because it has interesting properties. The variance in the electric field is a function of time now, and at certain instants of time, the variance in the electric field is less than what you can obtain in vacuum state. So this can lead to a state of light in which at certain instants of time, the noise is less than what you can achieve with vacuum. And these are called the squeeze states. Okay.